Hello, Physics Nation. My name is Nate Larmond, and I'd like to achieve equilibrium. How do we get this system to be balanced? When I let go, it is not in equilibrium, it's accelerating. So, what does equilibrium look like? Well, it's going to move with a constant velocity. This is a quarter. A quarter has a mass of 5 2/3 grams. So, the weight, this hanging weight, is changed into the horizontal tension by this pulley right here. That's what pulleys do, change the direction of forces. Except there's a backwards force on this sled. It's friction. The sled is grinding against this plastic. So it's not big enough. We have a little horizontal tug of war. The tension is greater than the friction force. How do we increase the friction force? Well, what if we throw a quarter into the sled? Still accelerating. Let's throw another quarter in. Oh, still accelerating. A third quarter. That's pretty close, actually. It's still accelerating, but I think if we throw a fourth quarter in, it's too much. Now, the backwards friction force is more than this tension. Except we're trying to make a proportion, a ratio. We're trying to compare the tension to the normal force. The normal force is the upwards force provided by the surface. Normal just means perpendicular. The surface is horizontal, and the force is vertical. So, like I said, we're trying to compare these two forces with a proportion, but the trouble is, these are mass standards. I know how much mass the quarter is. I don't know how much mass the box is. So we're actually going to take a little detour and use the original pulley for the elevator counterbalance, or Atwood's experiment. And we're going to try to measure the mass of my sled real quickly. So I've got the quarter hanging on one side and the sled hanging on the other. And whoa, when I let go, it's pretty clear who's winning this tug of war. Whoa, the box. The box is winning this tug of war. So, oops. It's hard to keep the string in my cardboard masking tape paperclip pulley. I'm trying to make it work here. But you can see when I let this system go, the box wins. So let's not do one quarter. Let's try 2 quarters in here. Remember, each quarter is 5 2/3 grams, so this is now roughly 11 grams. 11 1/3, I guess. Now let's set the system into motion. See, it's almost in equilibrium. When I push the quarters down, when I push the quarters down, they roughly move with a constant velocity. But when I push the box down, it decelerates. So that means these guys are a little bit heavier than the box. So let's just say the box is 11 grams. That is, it has a mass of 11 grams. We're trying to compare this to this. Now we know the mystery mass, the mass of the box. And maybe a hanging quarter is too severe of a weight. Maybe we should swap out the hanging quarter with a dime. All right, so let's try one thin dime. A dime has a mass of 2.27 grams. So let's try that as our new accelerating force. What's so magical about dynamic equilibrium? I don't know. See, friction's really inconsistent, like I said, and so when you can get a consistent phenomenon with an inconsistent system, it's just magic. It's just physics magic. Anyway, we have achieved dynamic equilibrium. What does that mean? Well, the ratio of the friction force to the normal force is roughly 0.2. That is, the weight is 5 times bigger than the friction force. And that proportion is called the coefficient of friction, or mu. But will that remain constant.